When talking about electricity, more people will not think about the magnetism, they will think only about the electric circuit and materials. We may feel familiar and have heard about the functions and rules of transformers, sinusoid, and relay. Interestingly, all these devices contain a magnetic material that are used to shape and conduct the magnetic field, which act like a medium in energy conversion process. By using magnetic materials in electrical machines, we will be able to reduce the size of machines significantly. This is there will be high flux density in the machine, resulting in large torque or large machine output per unit machine volume. I will tell you the fundamental concept why magnetic materials do form a major part in electrical machine. I will introduce you to magnetic circuit, its equivalent circuit, and some equations. This is a picture of toroid. As current flows through the coil, there will be magnetic flux, mostly in the coil. Some of the flux outside the toroid is called leakage flux. According to the path of the toroid in radius, the magnetic intensity of this path is shown here according to Ampere's circuit law. Closed integral H dot dl equal to Ni, HL equal to Ni, H2 pi r equal to Ni. 2 pi r is the circumference of the toroid. Ni is the magnetomotive force mmf in units of ampere turn. And here HL is equal to Ni, which equals to F, and we derive it again. According to HL equal to Ni, now we will obtain that H equal to N over Li ampere turn per meter. From B equal to mu H, and we derived again that B equal to mu Ni over L in Tesla. If we assume that there is no leakage flux outside the toroid, here's the equation of the flux crossing the cross-section of the toroid. Flux equal to integrate of B dot dA and equal to BA in Weber, where B is the average flux density in the core and A is the cross-sectional area of the toroid. From B equal to mu Ni over L and flux equal to BA, we will get that flux equal to mu Ni over LA equal to Ni over L over mu A, which equal to Ni over R. And here is the equivalent magnetic circuit. With equivalent magnetic circuit, it will be easier for us to do the calculations. If we increase the amount of current, magnetic intensity in the core will increase, and flux density in the core will change. I will show you the figure here. When the magnetic intensity is low, the flux density will increase approximately in linear curve. However, with higher values of magnetic intensity, flux density will become nonlinear. This graph shows effect of saturation of different materials. This graph is called the magnetization curve. In practice, the rotor of electrical machine will be separated from the stator by air gap. Let me show you what is the air gap. In order to maintain the same flux density, more mmf is needed in the core. The core medium and air gap medium are represented by reluctances. Here are the equations. Rc equal to Lc over mu c Ac. Rc represents reluctance of the core. Rg equal to Lg over mu 0 Ag. Rg represents reluctance of the air gap, and mu0 is a constant. Then we will get flux equal to Ni over Rc plus Rg, and Ni equal to HcLc plus HgLg, where L is the length of the core for Lc and air gap for Lg. Then flux density will be obtained. We will get that flux density for Bc is flux C over Ac, and it will be the same for Bg, which is, and we'll get that Bg will be equal to flux G over Ag. In between the air gap there will be jumping flux, which is called the fringing flux. If we neglect the fringing flux, the cross-sectional area of the core and the air gap will be equal, which result in equal flux density between air gap and the core, which equal to flux over Ac. Coil that is wounded on a magnetic core is commonly used in electric circuits. This coil is represented by an ideal circuit and is called inductance. Here I will define flux linkage of coil per ampere. Flux linkage, which is lambda, equal to N flux. Inductance L equal to lambda over I, and I and lambda are directly proportional. From the first two equations, we will get that L equal to N flux over I equal to N BA over I equal to N mu HA over I equal to N mu HA over HL over N equal to N square L over mu A. To note that L over mu A equal to reluctance of magnetic path. So at last we get that L equal to N square over R. In hysteresis, there are some terms I will introduce to you. First, residual flux density, Br. When H is 0, the core will retain at this Br. This happens when magnetic intensity is slowly decreasing. Second, hysteresis loop, which is the circle of magnetization as nonlinear BH curve. Hysteresis is flux density lag magnetic intensity. I and flux are in the same function. Hysteresis loss equal to, which is pH equal to Kn B power n max F, where n equal to 1.5 to 2.5. K is a constant. B max is the maximum flux density. Hysteresis loss of power. It is the loss of power in core due to hysteresis effect. The size of hysteresis loop is directly proportional to hysteresis loss. In other words, the bigger the loop, the bigger the loss. According to Faraday's law, we will get that the voltage E across the coil is E equal to N delta flux over delta T.
Now I will give you more information about eddy current loss, which you already know a little bit from the previous chapter. Eddy current loss occurs when the flux density changes rapidly in the core. The time variation of flux encoded by the part generates induced voltage, and the current inside the core is eddy current. A power loss I square R will be caused by the eddy current and will appear as heat in the core, because core material has resistance. Eddy current can reduce in two ways. 1. Using a high resistivity core material. 2. Use a laminated core with an insulator. Core loss can calculate from this equation, where Ke is the constant value depend on the type of material and its lamination thickness. B is flux density, and F is the frequency. Next is about the core loss, which is the combination of the hysteresis loss and the eddy current loss. According to this graph, the static loop can occur when the current is varied slowly. The eddy current loss can be negligibly small. For the dynamic loop, it happens when the current changes rapidly, which makes the loop become broader because of a large number of eddy currents in the core. Now I will talk about the exciting current. Exciting current is the current that establishes the sinusoid flux in the core. This current is generated by the sinusoid voltage source. First is exciting current without hysteresis. The exciting current is non-sinusoidal. From this graph, exciting current in phase with the flux, but the fundamental component of exciting current lagging induced voltage by 90 degrees. At the next graph, there are only one line graph which doesn't have a hysteresis loop, so it doesn't have a power loss. For the exciting current with hysteresis, real exciting current is non-symmetrical with respect to voltage waveform, but is symmetrical with respect to induced voltage, whereas is one of the exciting current in phase with the flux, while the other in phase with induced voltage. If it doesn't have hysteresis, will equal to the exciting current. Lastly is about equivalent circuit of exciting current. For exciting current with hysteresis, the exciting coil can be represented by resistance. To represent the core loss and the magnetizing inductance, represent the magnetization of core. Meanwhile, the exciting winding in the exciting current without hysteresis can be represented by a pure inductance. We hope that this video will give you more understanding about SI unit, fundamental of electric and magnetic system, which play an important role in electrical machine.
With more understanding on electricity, we can apply it into real-life usages, and when there are problems, we will be able to solve the problems.